items in the curriculum, I shall spend about 5 to 10 minutes time to give you an overview of foundry technology or foundry business, international as well as in our country. Let's first go to the international scenario. I will be very brief. These are the 10 top casting producers in the world. And you can see India in the third position. First position, China. Next is USA. In fact, there has been quite a number of times USA in the third position, India in the second, and so on. It has been changing. Ultimately, what do you think within next 3-4 years, India would permanently take place in the second position? And to surpass China is next to impossible, because you can see the difference. Volume of production is very, very wide and far, far ahead. Now let's come to the Indian scenario. We have about 4,500 to 5,000 foundries throughout the country. Out of these, about 80% is small, medium, and very small. Number of foundries with ISO 9000 is about 600. Now it has gone to about 650. And number of very big foundries with world-class facility will be 10 to 12. And you see the black dots, those are the foundry clusters. It's more or less distributed throughout the country, but there are distinctly few places where you can see concentration of, like here in West Bengal, Howrah belt. Then here in Gujarat, this is Rajkot belt. Here is Coimbatore belt. Here Belgaum and Belgaum belt, and there are few here. Kolhapur, Belgaum and Kolhapur together, there is a belt. And there is another cluster here. And rest of the places in country, they might have one or two. Mostly, these are the few places where foundry industry is concentrated. You can see the figures. West Bengal is still at the top with 18%. Gujarat 16, and so on. I shall show you the pie chart. This is the situation. This is the pictorial presentation of the foundry clusters throughout the country. This is of course outside your curriculum. This is for your general knowledge. You should know that where India stands so far as casting production is concerned. It's not a joke. India is either in the second position or third position. Now, what is a foundry? You all know probably. You have been taught. I understand. So I am not going into it. I shall give you a pictorial where you can see there are 3 lines coming from the top. Right hand one is melting. It's showing a symbol of cupola. Left hand one is this is sand mixer, Muller, and this is porcelain mixer. Now what we need a pattern where this is the pattern where there are 2 boxes, open and drag, and we fill it up with molding sand. And if it is a hollow casting, we need a core. Core is prepared from porcelain, and after the pattern is removed from the mold, this core is inserted here. So you have a cavity like this, and then you take the molten metal from the furnace with a ladle, pour into the cavity, and you have a casting shown in red. and then when it solidifies, you get the mold and take the casting out. These are what we call runners and risers. It goes back into the furnace for melting. This box is recycled here, and the sand again is recycled. So it's a complete cycle. Now you can see from here there are three major activities. One is melting, molding, and forming. These are the three processes is included in your curriculum, and I shall go by that. I shall first take up melting. Now, as you can see, this is summarizing the basic operations of a foundry is melting, molding. Can you hear me? Coat making, pouring, demolding, fettling, then recycling of metal, recycling of sand. You can take it down. And if you want, you can take down the flow diagram also. Shall I go back to the flow diagram?
Yes, sir.
You can just make line sketches.
In the sand, what goes mixed?
Aggregate.
The mixture in which the coarse sand is mixed.
The middle one is coarse sand, mixture. And this is Muller, that is it. It's called. This is cupola, and this is ladle. Let's make a quick line sketch. You all visited some foundry, I believe.
Yes, sir.
Kiswa.
I will.
You have seen cupola or reduction furnace? Not cupola. They had cupola earlier. Very deep, nice cupola. Okay. Then there are two types of forms. This one. This one. Now, there are distinctly two types of foundries. One is ferrous foundry, another is non-ferrous foundry. Non-ferrous means aluminium, copper, brass, bronze, and different alloys. Done? And there are two types of castings, sand castings and die castings. Most of the casting these days, aluminium casting is done in a die. Die means common in mold, made out of metal. But we shall concentrate on ferrous melting, ferrous foundry. Now, these are the melting furnaces that are used in foundries. Have you seen cupola, anybody?
Yes, sir.
No.
Yes, sir.
You have seen rotary melting furnace? It's not in your curriculum, therefore I have not colored it. Electric arc furnace, you haven't, but you have seen induction furnace.
Electric arc.
So I shall go over to first cupola. See, when people or mankind, they learn to melt iron, they first of all learn to melt bronze in the beginning. as it is called Bronze Age, you must have heard. So bronze was first people could make and melt and make casting out of it. Then that technology was adopted for melting cast iron or extracting cast iron from iron ore and make castings. Now, China is a pioneer one who borrowed the foundry technology from Middle East and steppe area, and they modified it to make it suitable for melting cast iron. Now, in the beginning, there was no cupola. They extracted iron from iron ore in a furnace which is very similar to our blast furnace as we use these days, and castings were made directly from that. Whereas cupola is a furnace where you remelt the cast iron and for doing the casting. So when in the beginning the use was limited, but when the cast iron use increased, then we felt the necessity of remelting the iron which was obtained from blast furnace. That's how cupola was evolved. The first patent of cupola was granted to John Wilkinson of UK in 1794. You can take it down. In interview, we may be asked this question. Cupola is normally fired with coke. This is the cupola, picture of a cupola, small cupola. As you can see, a man is standing here, so you can have an idea of the scale. How big is it? That's how a cupola looks like. Those who you haven't seen a cupola in real life, so you have some idea as to how it looks like. This is a very small one. It can be much bigger in diameter and also in height. I shall explain how the parts of cupola and different operations and functions. Cupola is a hollow cylinder made out of high steel sheet, maybe 6 to 10 mm diameter depending on the size of the cupola, which stands on a thick steel or cast iron base plate. The base plate has an opening at the bottom, which can be again closed with swing doors and which can be again dropped. And there is wing box. This is the wing box and this is the base plate. Through the wing box, we blow air. As you can see, these are two airs here. Through this we blow air to the furnace, where for combustion we need oxygen. And this air is blown from blower or fan, as we call it. This is the cross-sectional view of a cupola. I shall show you a better picture afterwards. Cupola is lined with, because there is hot metal inside, so on mild steel you cannot do it. There has to be a lining, refractory lining. So lining is from 6 inch to 9 inch thick, depending on the size. And in the melting zone, it is lined with ISA debris, which contains about 38% alumina. You can take it down. And the slab above the melting zone is lined with inferior quality of refractory, maybe IS6. The bottom is prepared on the base plate. We first close the door, put a prop, and then we make the arc by molding sand and making it slightly tapering or sloping towards the gate, towards the tapping spout, so that we can easily tap the molten metal which will accumulate on the arc. This is how a cupola looks like. As you can see, this is coke, then this is a layer of iron, then again coke, iron, coke, etc., etc. And this is charged up to, this is the full cupola shell. Above that it says stack or chimney. I shall show you a close-up view of this. As you can see, this is the swing door, half circle, which is closed and kept in place by a prop like this. This is tapping spout. As you can see, heart is made of sand and it is sloping this side. This is the tapping spout and this is the slag spout, because slag will float on the molten metal. It's lighter than the molten metal. So slag is removed from this and molten metal is taken from this. This is the wind box. These are the tuyers, and these are the layers of coke, iron, coke, etc. And besides coke and iron, we need fluxing element, which is normally limestone, or sometimes limestone mixed with dolostone, means dolomitic limestone. Dolomite is also added with limestone to form a slab. If you want, you can take this sketch, make a simple sketch of it.
What's the cause of mixing the limestone?
Beg pardon? Somebody asked some question?
So what is the cause of mixing the limestone? What is the cause of mixing the limestone?
Limestone. Limestone is a fluxing agent which will make slag by absorbing unwanted material in the charge. It will purify the material, molten metal, and form a slag. It's a very normal thing in all metal melting. While melting, a slag will form which contains either the oxide of the metal or some undesirable element, etc., etc. And that is to be removed from the system.
Limestone, what do you use? Economic limestone is
Limestone is the main element. As I told you, sometimes dolomitic limestone is also added, but very small quantity. Anybody making sketch?
Yes, sir.
Shall I go over to the next slide?
Yes, sir.
Next slide. After the sand bed is prepared, fire is lit with wooden chip and coke is added slowly up to the tuyer. First of all, when the heart is prepared, some wooden chip you place here and light up. And when the fire is normal, then you go on adding the coke up to this, up to tuyer. This portion is called bed coke. It generally doesn't go into the reaction with anything. It is recovered also to some extent. When the coke is well alight, more coke is added to reach the required level. Then the layers of coke metal flux are charged in layers till the cupola is full. Metal to coke ratio is on the average 7:1. That means 7 kg of charge will require 1 kg of coke.